This is the third installment of the Special Relativity series on special relativity topics done in more modern manners and more mathematical manners. This particular lecture is about relativistic velocities. So today we have a Lorentz transformation in the first sequence, and the second of the sequence was on metrics. And that's needed in particular in this section to talk about relativistic velocities. So what are these things? Let's get into this. So we're going to do three things in this lecture. One, we're going to talk about relativistic three velocities. The three refers to the fact that a velocity has three components, and it's the normal one that we think about when we look out and we see something moving. It has a direction, and it has a magnitude called speed. So I might refer to the speed as a three-speed. However, special relativity is about space-time, and so we'll be introduced to the Minkowski space-time and the metrics, etc. there that are used to measure distances in 4 space, not 3 space. That'll now be, you'll add in that extra spatial component. And since special relativity is formulated in this 4 space, we need to be able to talk about things like, well, what are velocities in 4 space? What are momentum in 4 space? What is angular momentum, for that matter, or anything else? That anything in physics that we know has to be extended into this 4 space regime. So let's get down to it. Let's talk about relativistic three velocities first. So we have these two frames, K and K prime. So again, I'm going to start talking about two frames, and we're going to have the two frames are moving with respect to each other, and this is a constant speed between the frames. All right. And if I am an observer, if I'm sitting in frame K, I might observe an object that is moving with a velocity lowercase v of t here. And by that, it might be changing. It might be switching directions. It might be increasing in magnitude. But it's the time derivative of the position, the Cartesian coordinates. There's supposed to be a 3 here. But so this is the standard definition of velocity in 3 space in frame K. Well, to an observer watching the very same thing in a different frame K prime, they have their own time T prime, which is related to the T in K. And so as a result, you will in general see the velocity as being something different than the observer in K. So we'd like to know how to get formulas to change from velocities observed in K to velocities, the same velocities observed in K prime. And for that, we start here in the middle of the page. We start with the component form of the Lorentz transformation. So we've seen this already, and this is the way that you convert from prime coordinates to non-prime coordinates. And these two expressions are always true. So to do the conversion, what we're going to do is we're going to take the time derivatives of both of these two expressions here. So these things, they can take the derivative of the first equation in t, recognizing that on the right side, t prime and x1 prime both depend on t. So when I take the derivative, they don't go away. There's some unknown derivatives. The same with taking the time derivative of x1. So let's take this, the first equation. If I take the time derivative of this first equation, I get this first blue equation below. Time derivative of t and t is 1, and then dt prime dt, I don't know what that is, but it's something. And dx1 dt is also something. And then I take the derivative of the second equation. Well, the time derivative of x1 with respect to time t is actually the first component of the velocity. So velocity of the first component of this velocity is dx1 dt. So that means this left-hand side is the actual v1 in frame k. And then I take the derivative of the right-hand side over here. So what happens, I got two equations here, and I ran up to these two blue equations. And what are they for? You think of them as a linear system of equations for these derivatives. You've got a dt prime dt and a dx1 prime dt, and there's two equations for these two unknowns, so you solve them. You find out what those are. That's just linear algebra. You find the answer, and you find at the top of this page, you find these equations in black. This is what you get for dt prime dt and dx1 prime dt. Neither of these are what we need to find the velocities in k prime. In particular, dx1 prime dt, that says what's the rate of change of x1 prime with respect to the time in the other frame. What we want is we want dx in here. What we really want is we want to know what dx1 prime dt prime is, because I have to use the t in the frame I'm talking about. So that's this first expression here. I'm going to highlight this first expression in blue. So the v1 prime is dx1 prime dt prime, which by the chain rule is dx1 prime dt, dt prime. Well, both of these terms here can be replaced by using the expressions above. In particular, this dt prime, or dt, this is 1 over that. And dx1 prime dt is just this expression on the top. So basically, you're going to divide these two things to get the dx1 prime dt prime. And you get this formula here. And for the other velocities, you do the same thing. It's dk. So I've got the 2 and 3 components of the velocity, and I use the same formulas up here to convert them, and I get something slightly different because this first expression is just v2. If k is 2, if k is 3 here, this would be v3. So in summary, these blue things, what I got one, this is one equation, and this is actually two equations for k is equal to 2 and 3. So I'll summarize that, and this is this theorem stated below. It says, this tells you if I know the velocities of the objects in my k frame, and k is moving at a constant speed v with respect to k prime. But so in k, I see what v1 and v2 and v3 are, and I want to know what the observer in k prime sees. This is how we convert from velocities in k to velocities in k prime. Now, this creates a lot of issues. It's not easy at all to convert velocities in our normal sense from one frame to the other. And these formulas are not, in particular, they're not linear. They're the way that v1 prime depends on v1. You can see there's a v1 sitting there, and there's a v1 down here in the denominator. So this is not easy. You can't do matrices or anything for this. So I'm going to point out what's bad about, although we do know how to convert velocities from one frame to the other, these three velocities, they're hard to work with and essentially meaningless to develop theory with. But let's go ahead and see what we can say about this. The things we can say is that the relationship is nonlinear. And if you looked at those formulas, it's pretty clear that if you add two velocities in k frame, it is in no way the sum of the same two velocities in the other frame. So none of this works in an intuitive way at all. You got nonlinear relationship. The fact that velocities, adding velocities is normally invariant, is not true anymore. And also, if you looked at the expressions for everything, for the V1, V2, V3s, and you try to compute, let's say you try to compute the magnitude, which would be the 3 speed, you'd find out that the magnitude in the K frame is not the same as the magnitude in the K prime frame. So speeds change. They're not the same in each frame. And here's explicitly, if you do it, you get this big expression. It's ugly and messy. And what's really bad about this is that this thing squared, this term here squared, is what you need to describe classical kinetic energy. So classical kinetic energy is 1/2 mass times velocity squared. Well, if I wanted to have 1/2 mass times velocity squared in K prime, that in no way is going to be equal to 1/2 mv squared in the K frame. So what this means is what? Well, the relationship between three velocities is hard. Velocities don't add. Speeds are different. And as a consequence, kinetic energy cannot be defined that way. Kinetic energy, classical kinetic energy, is no longer relativistic kinetic energy. So, what do? Well, this is where we go on a long tangent. Over years, people decided that the best way to deal with dynamics in relativity is to use something called Minkowski space. Now, we've already been introduced to the coordinate systems in Minkowski space. It's basically the same. You use the spatial coordinates in your reference frame, but instead of using time on the first component, you use c times t, so that has units of space. So this is strictly spatial components in a 4 space. And you can have basis vectors for each of the components as well, so you can write this out that way. Well, if you have these basis vectors and you go to the second frame, you go to the second talk on metrics. What you need for the extrinsic approach to decide what distances are, or getting a metric, is you need to know what the inner product is between these basis vectors. So this is where it gets kind of weird and kind of wrong. In Minkowski space, the inner product of the basis vectors is defined. It's defined in the following way: that if I take two like basis vectors and I inner product them, they're one only if I'm taking E naught with E naught. So if I've got a naught here and a naught here, that's taking E naught dot with E naught in the Minkowski sense, and I get a 1. But when I do that with the space ones, like E1 dot E1 with this Minkowski inner product, I get -1. And all other possible dot products or Minkowski inner products are going to be 0. Well, this, if you're a mathematician and you look at this definition, this is just wrong. What's wrong about it? Well, you can't have an inner product of a vector with itself being negative. So technically, in math, what this is called, it's called a pseudo inner product. But when you look at relativity literature, they make you believe that it's actually an inner product. It's not. And the reason is that if it looks like an inner product, then they can talk about all sorts of extra things, like the metric tensor. And if you you take the theory in the second lecture and you work out what the metric tensor is based on these inner products, you get this matrix with some diagonal entries. So that's the space-time metric in Minkowski space. Is that actually a metric tensor? Not really. But it looks and acts like it when you manipulate things. If you have a metric, you can also now find the norm or the length of things. So here's a vector S that's in this space. It's a four-dimensional space-time. And the way that you define a norm with regard to the metric is you do the inner product of the vector with itself and then take the square root. In this case, for this metric tensor, S being the Minkowski norm of the Minkowski coordinate is this square root expression over here. And you look at that and you think, well, there's some minus signs in there and there's a plus sign. Sometimes the thing under the square root will be positive. Sometimes the things under the square root will be negative. That produces some weird things. But it's clear that, so this is basically what the equivalent of Pythagoras theorem is in special relativity. Instead of all pluses, you got three minuses with the spatial coordinates and a plus sign with the temporal part. If you're a mathematician, you would say, oh, great, I have a norm. And everyone who knows this, if you have a norm in some space, then you can define something called a metric. And the metric is defined in this manner. It should be defined as you take the difference between the two objects and you find the length of the difference between the objects based on what your norm is. Again, this is a pseudo-metric. It's not actually a metric. And one of the reasons it's not an actual metric, again, is because if you take the metric of the vector with itself, sometimes you get these negative numbers. And metrics are always supposed to be positive. So this is the layout for the Minkowski inner product, metric tensor, and norm, and what they are and what they are not. If that S squared term in the previous slide is positive, the terminology is that the coordinate is time-like. If it's zero, it's space-like. If it's less than zero, this is a nonsensical expression, by the way, S squared less than zero. We'll get imaginary numbers, and how are you going to interpret that? That's hard, but they still refer to that as space-like. Most of the action really occurs in these first two scenarios. And if you look at the formula for S squared, S equals 0 is actually the equation of a cone in a high-dimensional space. And reality sits inside the cone, and anything that travels the speed of light sits on the cone itself. And to show you this more clearly, let's just say I set the coordinates x2 and x3 equal to 0. What do these constant S curves look like? Well, they're hyperbole. They're things like this, and you have this S squared is c squared t squared minus x1 squared. So the equation for that in the xt plane is a hyperbola. So if I set S equal to 1, I get one of these hyperbola. If I set S equal to 2, I get a different hyperbola. So there's a family of hyperbola which wherever we're on there, S is constant. And that describes everything within the cone. The cone here is this looks like an absolute value sign here. And so that's what these S equal constant curves look like in one dimension. If you go to two dimensions, let's say you go down here and say, let's just set one of these coordinates x3 equal to 0, then you get a formula in 3 space, which when you look at that, that's a 2-sheet hyperboloid. So it's basically you take the picture in the graph above and you rotate it around one of the axes and you get these bowl-shaped hyperboloids on which S is constant. All right. What's key in this thing is that this quantity of where on these hyperboloids where S is a constant, this S does not, it is invariant under Lorentz transformations. What that means is that S squared in K coordinates will equal S prime squared in K prime coordinates. So regardless of what frame you are in measuring these things in, the S values will be the same. So it's important to find invariance under Lorentz transformations. That means these are things that are the same in whether you're in the non-moving frame or the moving frame. It doesn't matter. They have the same values. And a proof of this is given below. So what's S prime squared? It's the Minkowski metric of S prime squared, which, using the previous slide, that is just this expression where you sum in the mu's and nu's. This is a tensor double sum, so this sum in the indices is implied. And that basically is just for this metric tensor, it's just this expression. So that's what we get. So the length is the square root of this. So then you use the everywhere you see a prime in here, you use the Lorentz transformation. You input what the non-prime equivalents are. So for example, this first term here this is T prime, what I've got highlighted here. This is T prime by the Lorentz transformation. There's also an X prime. This would be what X prime is with respect to T and X1. I can expand this out and cancel things, and it turns out that when you just expand this whole thing out and cancel, you get this expression, which is, by definition, the length in the Minkowski sense squared. So this is S squared equals S prime squared. Proof, period. Next thing that's done to describe dynamics is we need a better notion of time. To get a notion of time in force space, we define something called the proper time, which is an offshoot of inertial proper time, which I talked about before. What this is so it's defined in this manner. Why is it defined this way? So proper time tau is the time that is measured in the moving frame while this object is moving with regard to k. So k measures a velocity v vector of t. And from that, I can compute this thing in frame k. I can say, okay, I see the velocity. I compute this integral, and I'm going to call that the proper time, where this gamma sub v is using not the inertial velocity between frames, but the velocity as observed in k. And there's this integral expression. So what's the big deal about this? Well, the big deal is it's a generalization of the inertial proper time, because if it turned out that the thing that you were observing in k had this velocity v, and this velocity v was a constant velocity, then the whole thing collapses down to the previous inertial time. And the inertial time, as we know, is the time that the person in the moving frame sees. So this tau is the time that is being measured in the frame that's moving with the object. And that would be even if that motion was not constant. And so you can say, look, if I have different events in space-time and they have different times, so I have two events in four-dimensional space, P1 and P2, they have their time coordinates and they have their space coordinates for these events. I can compute the proper time difference between the events, and that's simply this integral. And there's a lot of different ways to write this expression. It gets kind of, the notation in special relativity gets quite hairy. But basically, so I'll go through this one line on the bottom. So the duration between events is you look at you look at the motion in space-time and you integrate in with respect to proper time. You can convert that to a length integral. So these are the length elements in space-time divided by c, which is constant. And this length element is given by the metric for the problem, which is a Minkowski metric, which you can write out explicitly in the following way, where again, if I have a repeated index, that means a sum. And if you look at this sum here, that gives me velocity squared dt if I pull out the dt from the square root sign. So delta tau on the one hand is given by this integral, but what it really is it's this scaled length in space-time. It's the length and the curve, the curvy motion of the particle divided the length in the Minkowski length sense divided by c. So that's time. And what's a little mathematical side note is that this integrand here is positive, and as t changes, that means this is going to be an increasing function of t. So tau is an increasing function of t. I don't have a formula for it unless I know what v is. But because it's an strictly increasing function of t, that means that there's an inverse. That means that if I could do this integral, and I found out what it was for t, I can get a tau. Conversely, if I know what tau is, I could find what t is. All right. So this is an interesting little sidebar. You hear a lot of stuff about this on different videos and different discussions. You hear people saying you cannot exceed the speed of light. So the question is, can I be an observer in k, and can I watch some object v of t that has this 3 speed that's bigger than c? That's the question. So this is not something that you derive. This is actually an axiom. The axiom goes like this. It's that if I see an object with a speed that's initially, at time t equals 0, the speed is initially less than c, then the axiom is that going to be that for it to be reality, we're going to assume then that the velocity is always less than c for the rest of time. What that means, if you think about it, it means that if you start off as being a time-like trajectory in space-time, so I'm going to illustrate this down below here. This bottom axis gray thing here is this is x1 and x2 in space, just to make the diagram manageable. This is our light cone. Reality for having s squared positive is everything inside this. And the motion of objects are described by curves that lie inside this light cone. I've drawn two different ones here. This straight line from the origin to point P, it's a straight line, that's a constant speed object sitting in there, and it remains in the cone forever. Well, the question might be, well, there's other possible curves within here. Are they realistic? Well, this one here I claim is not. And the reason it isn't is for the following. So maybe this is describing the motion of a particle, and it comes up here, and you see, as you follow this, it starts to move up in the y direction without x changing. So as this comes up, it becomes almost horizontal, and x is not changing. Well, almost horizontal means an enormous speed, way bigger than c. So this thing has got a y component of velocity, which is huge, and an x component of velocity, which is almost 0, making the combined speed huge. So this particular world line violates this axiom. So it's not something you would see, even though the entire world line sits within this cone. So it's not enough just to say if it sits in the cone, it's allowable. It has to sit in the cone and still obey this inequality. So how do we actually deal with velocities in some sensible manner? So this is actually quite useful. You want to talk about dynamics in space-time. Space-time is a four-dimensional thing, so we really need a four-dimensional velocity through space-time. And when I say space-time here, I'll always be referring to the Minkowski coordinates. I could make a definition of velocity any way I like. I could have had, say, a velocity in four-dimensional velocity equal to the rate of change of Minkowski in time t. But that has some disadvantages. You could do that, but it turns out that there's a good reason to make the velocity rate of change not with respect to your own time and t, but make it the rate of change of the position with respect to the proper time of the object. That would be the object's clock. So the object is moving, it's changing its velocity, and therefore the proper time is changing as t moves on. But we know this tau is the time with respect to the moving object. So we're going to define for velocity to be the position change in spacetime with respect to proper time of the object. In the other frame k prime, it will be the position in k prime with respect to the proper time. So they're slightly different. So there's the four velocity in k, and there's the corresponding four velocity in k prime, and they're both respect to proper time. A consequence of this is this following invariant theorem here. It says that if I have two different inertial frames, I have whatever the velocity is of the object that I see in k, doesn't matter what it is, and I compute these things, it turns out that the Minkowski norms of these quantities is c. This comes up with sort of a sensational kind of conclusion in special relativity, which is that the force speed of any object is always the speed of light. So it sounds thrilling, that this force speed is the same. Doesn't matter what you do. You're always going the same speed. But that's not what our experience is. This is just really a mathematical artifact. These aren't real norms. These are Minkowski norms. But it's still useful to keep track of things that are invariant between a reference frames. So it's good to know that we've made a definition of for velocity that has the same force speed in every inertial frame. How does that proof go? Here we go. So ds d tau is ds dt dt d tau. We know from the definition of tau that this derivative can be represented by 1 over the integrand, which is this gamma. This is now ds dt. And s, I know what it is. It's got c, x1, x2, x3. I take the time derivatives, and what I get is this expression here is this gamma times c, this gamma times the v1 component, gamma times v2, gamma times v3. So I get a way of parsing out this 4 vector. It's got basically a part that has the first part, which is the temporal part, has the c in there. All the spatial elements have the normal 3 velocity sitting in there. So for velocity is this factor c times this vector, where this v is the 3 velocity. If you simply take this vector and you find its Minkowski norm, you get this expression here, and you can just do algebra and simplify it, saying, look at Minkowski norm squared, turns out to be c squared. What does that mean? That means the norm of u is just c. You take square root of both sides. Well, more than that, u prime is the rate of change in proper time of S prime. And S prime is computed using the Lorentz transformation matrix lambda. So I can put a lambda S in there. Lambda, because the frames are inertial, is a constant matrix, so I can pull it out and I get the matrix times ds d tau, which is simply, by definition, the lambda matrix times the force velocity in k. So this says if I know the force velocity in k, I can compute it in k prime by just matrix multiplying by the Lorentz matrix. So there's a theorem that says that if I have two four vectors that are related by the Lorentz matrix, then their Minkowski norm is automatically invariant. That's a fact for any two vectors in different frames. So if I had an A vector representing anything here times the Lorentz matrix to get an A prime vector in the other frame, the lengths of those things will be invariant. So this tells us that I now have a way of talking about velocities in force space, in space-time. I know that the speeds of these things that I observe are the same in either frame, and I know how to convert between velocities in k and k prime very easily. It's not like the initial transparency I had. And so that's the end of this proof. If you read it, it says, well, I need the invariance theorem, and I'll simply put this transparency up to indicate what I had said verbally just before, that if I have any two vectors related by the Lorentz matrix, then their norms are going to be the same, and below here is the proof. And you can read this at your own leisure. That's just simply needed to complete the previous proof that the force speed is the same in every reference frame. That's the end of this. This is an introduction to velocity. Now that we have for velocity, we can talk about momentum in force space, and then eventually energy in force space. With that, we end this lecture.